welcome you all for the NPTEL online course on Smart Grid. And today we will be discussing mainly on the execution of all the concepts that we have learned throughout the course, how it can be implemented on a hardware platform with help of an existing test bed. Now, the concern here, when we like to exercise any concept like your energy management, whether it is bit grid or islanded mode of operation, whether the system is at peak operation or off peak operation, as well as all this HIL, hardware in loop experimentation, both in control strategy as well as in power mode, can be analyzed in detail. Now, all the listeners, my personal request here, what I am going to present in today's discussion belongs to our laboratory, where we have created a very smart grid laboratory, and all my simulations results are based on the outcome of the existing lab, which is currently functional at Indian Institute of Technology, Roorkee. Now, we will be focusing on design of smart grid and practical smart grid case studies. So, first of all, we will see how the smart grid has been developed, and then we will take all the simulation studies into a real time simulation with hardware setup and analyze those results. Now, this is how actually the lab look like. So, I mean, you can just see that this is mainly the RTDS of 6 rack, and we can say this is the power amplifier, and then we have the smart grid hardware test bench. Now, all the three, that is RTDS, power amplifier and the test bed on smart grid, being connected and simulated simultaneously. Now, let us understand what are the devices currently available in the laboratory, smart grid laboratory. So, the hardware facilities available in our smart grid lab, we do have a RTDS which is of 6 rack, PB5 processor, GTAO based, GTDO based, GTDI and GTAI card based RTDS. And the very important part, the RTDS can simulate a system which is a maximum of 432 nodes. Then we have second important device to our laboratory, which is power amplifier, and the rating, which is 5 kVA continuous. It can, perhaps the capacity of the amplifier can be increased to 10 kVA for a short time, and it can go as high as 40 kilovolt ampere for a few short duration of peak hours. Now, this amplifier, which is support power hardware in loop experimentation, that is PHIL, it has a high accuracy voltage and current measurement for power hardware loop simulation. It supports the AC microgrid up to 270 volts RMS in each phase, okay. And though we do not operate beyond 250 volt at a given time, but it has the capacity, when the phase voltage goes as high as 270, still it can be made operational. Now, the DC microgrid, if you like to connect this amplifier, then it can accommodate up to 400 volt DC. Now, it has the capacity to operate in all 4 quadrant, and then finally, it has the ability to handle 0 lead, 0 lag and unity power factor operations. Now, we do have sources, energy sources. The first one is PV emulator, which will mimic your solar PV, and we have connected 2 kilowatt PV emulator to imitate the actual behavior of a PV solar. It has the capacity to accommodate the shading effect. Real world weather simulation is possible. Static and dynamic MPPT testing also can be performed with this emulator. So, as a whole I can say 4 kilowatt of emulator in place. Now, we do have a wind emulator which can again mimic your wind renewables, and it is based on DFIG and DFIG rated 2.2 kilowatt capacity, and it can simulate real wind simulation is possible, and we can track MPPT. That is good news. So, as a whole if you see the PV which is a 4 kilowatt and the wind of 2.2, at this moment it has been connected to the test bed. Now, then we have also connected real PV rooftop of 1 kilowatt, and we also do have a diesel generator of 3 kVA capacity, single phase and push button type. So, if you see the sources is as high as actually 4 kilowatt of PV and 2.2 for wind and 1 for rooftop and 3 for diesel. So, close to 10 kilowatt source has been connected to the test bed. So, I can say it's an interesting setup which is very nicely handle 10 kilowatt capacity. Now, we also do have storage sources, and the lead acid battery of capacity 60 ampere hour, and then we have ultra capacitor of 58 farad, and we can possibly investigate all type of storages. And we do connect approximately at a given time maybe 6 to 8 kilowatt of or the kVA of storage that can be connected to my test bed at any given time through battery. So, as a whole we can certainly test a test bed of 15 to 20 kilowatt capacity. Now, then coming back to loads, we very interestingly recently acquired a programmable load. I mean it is basically 3 single phase loads, and the power rating of each device is close to 1.5 kilowatt. So, total of 4.5 kilowatt load, and it can very interestingly operate at all 3 constant power, constant impedance and constant current load that can be implemented. And then going back to converters, we do have these converters are used for integration of sources as well as storage, and we have both DC-DC and AC-DC type converters, and we do have the converters which has the capability of both bidirectional and unidirectional capability inbuilt. Now, what is hardware in loop HIL experimentation? You must have heard about HIL experimentation of smart grid. You develop a concept, you simulate something, and then you try to assure, confirm your analysis or concept or validate it through an HIL experimentation. And in hardware in loop HIL simulation, hardware devices are interfaced in a real time simulator, that is RTS, which contain rest of the model necessary to test the device operation. So, through HIL we basically connect the hardware devices to your simulator, and most of the components are available within the simulator and few hardware devices that can be interfaced with your simulator. Now, HIL simulation, hardware in loop simulation, offer a very cost effective and safe method to test physical devices under real time operating conditions. HIL simulations are of 2 types. One is so called closed type. closed loop type and the other one is known as open loop type. And in case of open loop type, it is very interesting that where the signals are sent from the RTS to the device or most commonly, whereas in case of closed loop, the response of the device is fed back to my RTS. So, we do have two types of HIL, one is closed loop and the other one is open loop. In case of open loop, hardware in simulation during open loop where signals are sent from the real time simulator to the device. So, we have a simulator, so signals are sent from the simulator to the physical device. Whereas, in case of closed loop, the response that has been received from the device can be given back to the RTS. Now, there are two types of HIL. One is known as control hardware in loop and the other one is known as power hardware in loop. CHIL, control hardware in loop simulation, PHIL, power hardware in loop simulation. Now, in case of CHIL, physical control or protection relay devices are interfaced with the RTS and exchange digital and or analog signals. So, there is signals are exchanged, but no power. If you see the CHIL application, the signals can be exchanged at low voltage level around plus or minus 10 volts, allowing a straightforward interface with the RTDS using digital to analog and analog to digital converters. So, if you see this is my RTDS or the real time simulator, then we convert the output from D to A and that analog information will go to my amplifier and then to my device which is under test. Now, the outcome of the device now can go back from analog to digital conversion feedback to RTDS. So, this kind of setup is certainly a closed loop and it is control hardware in loop simulation with closed loop representation. In case of power hardware in loop simulation, PHIL simulation involves interfacing the simulator that is RTDS with a power device such as a motor, inverter, generator and transformer, and the real time simulator and the power device exchange power over the PHIL interface. So, the simulator and the device do exchange power which was not there in case of your control hardware in loop simulation, but in case of power hardware in loop simulation the devices could be either motor, transformer, inverter, converters, and there is a power exchange takes place between your device and the simulator. Now, the digital to analog DA converter includes as part of the RTDS provides analog signal scaled down to electronic level within plus or minus 10 volts and the amplifier are required in PHIL simulation to scale the signal sent from the RTDS to the DUT unit or your device unit. Now, please try to understand in case of PHIL we do need to have an amplifier and that amplifiers perhaps scale up your signal received from your simulator and give the amplifier signal to the device. Now, in case of PHIL simulation which requires complex circuitry and hardware maintenance compared to control hardware in loop simulation. Now, this is the closed loop setup of your PHIL. We can see this is my RTDS and we have scaled and then D to A converter and then through amplifier it has been given to my device which is under test and further At feedback, we can have voltage and current sensors in place, and then A to D conversion, and through filter we can give that output to my simulator. So, this is a closed loop where the amplifier do interface both your RTDS and the device could be your test bed too. Now, there are different case studies we have considered for discussion for this NPTEL course, where we will talk many case studies one by one, how it has been validated through hardware setup. In previous lectures we have discussed about simulations, and today we really talk about how they have been validated through a hardware test bed or a platform through both CHIL and PHIL experimentations. Now, first of all, power flow control strategies, that is your case study 1 we will be discussing. Then we will talk about case study 2 where isolated DC microgrid operation, and then we will take care of PHIL. We will consider a case study 3, that is DC microgrid integration to IIT Roorkee distribution system, and case number 4, coordinated voltage control for IEEE 33 bus system. So, these are the 4 case studies we will be focusing in detail during today's lecture. Now, when we see the power flow control strategies, in the initial stage, I think in the previous lecture also you might have seen the DC microgrid architecture. This is my utility grid, okay, and we had GSC, and this is my DC bus. We have loads connected and my PV, battery and ultra capacitor in place. We have also discussed the flow chart in our previous lecture. So, depending upon the grid situation, we can control your devices within the DC grid, so that the maximum stress on the utility can be avoided by optimally operating your storage devices to meet out the loads. So, by sensing different SOC points, one can easily allow its battery whether to charge or discharge, and similarly the PV and other connected devices such as supercapacitors. We have seen that there are different operating modes have been considered. So, one could be my peak mode of operation, and the other one could be the off peak mode of operation, and then finally we can consider the isolated mode of operation. Please try to understand the main objective of having DC microgrid or smart grid in place with my existing power system is to perhaps support or help the main grid to survive better, which was not possible earlier without smart grid. So, here one of the main objective, the system is always under stress, means the utility is under stress, because they do have different load characteristics, and when it is at peak point, then certainly the system is under stress because they are not able to cater all the loads connected during that particular hour. So, now we have couple of, let us say couple of microgrids, maybe 100 of microgrids, maybe millions of microgrid in place across the country after 5 to 10 years. So, if those microgrids, let us say, had bit of energy stored in their batteries, so instead of taking energy from the grid during peak hours, if they can survive themselves for some extent, then the grid will be completely relieved. And also during off peak hours, when the system is not at stress, so then if my battery status can be checked, and if the smart grid storage is already having huge storage, then it can manage its load, and if not, then it can draw energy from the main grid to charge the battery storages. Whereas going back to the third scenario, if the grid is not present to me, then also I can get some sort of comfort to meet my critical loads without the grid. So, that case, depending upon the storage capacity, we will keep on catering the loads, and if the battery discharge SOC is very low, maybe below 30% or below 20%, we will slowly keep on disconnecting the non-critical loads, and if required, finally, because the grid is not there, even the critical loads may be compromised. But if you do a proper design, certainly the critical loads can be protect it with a hope that the grid which is not available to you is not for a very long time. But if it is completely isolated remote area, then you have to design your network such that given a period of time of your application, you must be able to manage your critical loads at any given time of the day. When we come back for the next lecture, we will talk a few more applications on smart grid on hardware setup. Thank you.